Great. Well, welcome everybody. This is a small workshop today, kind of a niche topic, but welcome to our Introduction to Geospatial Python series. And I'll go ahead and pin myself as the speaker for the moment. Very exciting. I'm Genoa Stars. I'm a GIS programmer with the Informatics and GIS program, which I'll tell you a little bit about. And I'm here with Shane. You want to say hi, Shane? Uh,
Wait, I
and
muted
yeah,
myself. Hello, welcome everyone.
Yeah, we're here today to talk about a topic very near and dear to our heart, geospatial Python. Yay! Today will be a pretty broad overview. This is our first time teaching the workshop, so we are not quite sure where people are coming from in terms of their experience with both spatial data or ARC products and mapping and Python. So we've covered in this first session the broad strokes of both, and we'll get more into the details and the nitty-gritty of it in our second and third sessions, which will be specifically on coding in kind of an ArcGIS environment, and then coding in open source or GeoPandas. So those will be exciting, and those will be our week 2 and 3 sessions. Why is this doing this way? Here we go. I'm going to share my slides. Can you guys see this?
Yes, we can.
Yep.
Beautiful. So today's topic is Introduction to Geospatial Python. And session 1 is on kind of what is geospatial Python, what is geospatial data, and what are we talking about when we say using it in Python. But to back out one more step, who are we and why do we host this kind of workshop? The Informatics and GIS program, or IGIS, is a component of the University of California Agriculture and Natural Resources program. And this is kind of a not physical 11th UC campus. So Ag and Natural Resources is responsible for a lot of programs that help connect research to Californians on the land and in the environment. So this is things like 4-H, CalFresh, Master Gardeners, and then us, Informatics and GIS. So you've probably heard of a lot of these programs. We're also affiliated with research and extension centers, and of course, the amazing UC Cooperative Extension Program. Us in particular refers to our core team of 7 people here, our brave and fearless leader, Maggie Kelly, based at UC Berkeley. We have Andy, Sean, Shane, Robert, Priyanka, and I. And we offer a really wide variety of topics related to spatial data. This includes actual services, so things like building story maps, web apps, drone services, processing data, that kind of thing. Teaching workshops like this one on coding topics, on geospatial data topics. And we have a really intense, awesome workshop on drones, using drones and collecting and processing drone data called Drone Camp. And then we also, for those of you deep in projects and working on specific topics, we offer office hours or consultations on all of these topics where you can just sign up for free for a short slot of time to consult with somebody who has just a wealth of experience dealing with every issue under the sun. And speaking of spatial data, here is us georeferenced. So members of our team are kind of based throughout the state. We have people in Berkeley, we have people up in Hopland, folks down at Kearney. But right now, yes, our core is at the UC Berkeley campus. So this is an example of some geospatial data. We have not just information about people and presumably their advanced degrees, which is pretty funny to put on here. But then we also have a location attributed with where they are physically. So what is geospatial data? This is the heart of the issue, right? Most of us are familiar with data in the broad sense, but geospatial data in particular has the location of an object or grid in writing. So this can be coordinates, which you're probably familiar with, like an X or a Y. This can be an actual address, or it can be some other reference system, like even a zip code or a county is technically a spatial attribute, right? We can figure out where that location is. And these spatial data are the be all and end all. Their coordinates or information about where something is, but they're also a way of writing or representing spatial data. There's no way to actually tie something to a physical location, so writing is a way to represent that, right? And spatial data is near and dear to our heart because it is different and it has to be handled different than just kind of generic data and generic tables. So geographic data represents spatial locations and non-spatial information at certain times on the Earth, which is a pretty difficult thing to capture just in like a little table or data frame. It's based on these two continuous dimensions. So we have the surface going, but then it's also three-dimensional because it's on the surface of the Earth, or you could be doing astronomy, it could be somewhere in the universe. All of these are things that it's kind of hard to translate into writing. And spatial data also has this kind of unique feature of spatial dependency. So things that are closer to each other tend to be more similar than things that are further apart. And again, geographic data is in a 3D sense on the curved surface of the Earth. So all of these are things that when data formats for spatial data were being developed, when we think about how we're going to save or write or read or interpret information, these are all things that come into play. So I've said spatial data in written form. What does this actually look like? So we'll start with just talking about the two ways of thinking and recording spatial data. These are raster and vector. And you've probably encountered both of these before in your life and in your history. And if you haven't, let us know. Happy to talk about it more, and we will a little bit here. But raster data at the heart of it is kind of a grid system. So every time you look at something that has pixels or grids, we consider that more or less raster. And then projected over a continuous surface, whereas vector data is kind of explicit. It's talking about specific features, specific objects, kind of outlined or set as a point or a line. So raster data are kind of a list of numbers when they're stored as data with a starting point or a key anchor point referred to. So you can see here's a digital elevation model, I think. So we've got a bunch of cells, they're also called pixels, and each one has a value within representing some sort of information. So in this case, it would be height or elevation. And we have information on where to start our grid. And then it's just kind of listed at all these numbers. We have continuous rasters where the attribute is a number that's continuous. So elevation would be an example. But then we also have rasters where information is specific categories. So representational. In this case, here's like a national land cover data set. So we can see here the light green pixels that are coded as 1 represent grass, 2 is trees. 1 and 2 and 3 are not the actual values of the raster necessarily or the data, but they're telling us information about each cell in the grid anyways. And here are some cool examples of raster data. We have, like I said before, land cover data, which is categorical. We have a digital elevation model. You'll hear about these a lot, called DEMs, and this is a continuous data set. Every pixel over the surface is like ranging in this continuous number. And then we have things like Landsat and drone imagery, where each pixel is actually representing, has a value that represents the light waves that are coming off or being reflected by the surface of the Earth. So imagery is also considered raster data. Here's an example of how we tend to think of geospatial data in these kind of layers. And you can see here, the bottom two are examples of raster data, these kind of surfaces or grids or fields over the landscape. Now, a couple other examples would be climate data, raster graphics, scanned imagery, and often scanned maps will be considered raster data. Next, we have vector data, and this is a totally different way of thinking about things. We consider the spatial information explicit. We're talking about objects on the landscape. We're talking about points, polygons, lines, things that you can delineate and identify separately from each other. We're no longer talking about things kind of on this sliding scale anymore. And some terms associated with vector data are like objects, features, shapes, records. And vector data lends itself very well to a kind of table format. Some examples here, points. So sampling locations, trees, centroids, addresses. And the example I've provided here is actually points for iNaturalist sightings that people have provided. Lines are going to be, I'm sure you're very familiar with lines, but things like waterways or infrastructure, hydrography, contours, all sorts of things. And then polygons. So this is going to be things like a zip code or a county. There are infinite possibilities. I'm sure you can think of so many different types of polygon data. And that's one of the most familiar, I think, and one of the ones we see the most. Now, when we're thinking about this in Python, we've been thinking and looking here at this data represented in map form, right? And that's kind of where our brain goes first with geospatial data. But often when you're working with coding, you're going to start thinking about things a little bit more as a table. So here, taking a look at just this first data set in iNaturalist, with just 3 lines of code, I can take my data from these points into this kind of table format where I can see all this information laid out in front of me. And what makes it geospatial data is really this last column here. So this is a point data set. It has a column called shape. Sometimes it'll be called geometry. Sometimes it'll just be an X column and a Y column. But we have our attributes, so what is at that point of interest, and then we have the actual physical location of the data. So we've got coordinates, because this is a point data set. And then for some data, it'll include the coordinate system here, which is handy. In other cases, it won't. But if you are looking at a shape or geometry column, you are probably looking at a spatial data set. So for points, it looks pretty straightforward, right? We've got an X coordinate and a Y coordinate. This has a spot for Z, but there aren't any actual Z data present. That would be like elevation. So let's take a look at a line data set. It's a little more complicated, right? We're not just talking about individual points or X or Y's anymore. Now we also have some distance going on. We've got a lot of segmented points that make up a line and the space between them. And then again, we have some coordinate information down here at the end. So this is the Fish and Wildlife Service waterway map for the Tamalpais watershed. And then finally, that takes us to polygon, which is going to be kind of insane to look at. We've got points for all of our line segments within our polygon that make it up. And this is an example of why geospatial data gets so big so quickly. Is because you're no longer dealing with just single points. You're not dealing with small information. You're dealing with a lot of huge attributes that are stored in these data frames. And so that's part of why we have all these special softwares and special packages to be able to handle this sort of data. A little look behind the curtain here. Next, I'm going to touch on projections. Maybe you've heard of them, maybe you haven't. I'm going to play this short clip. If you can't hear anything, please let me know in the chat. But this is from the West Wing.
Can't hear anything yet. But you know we can't hear anything now.
Well, I might not actually know how to make sound play over Zoom, over YouTube.
You can try one thing. Go to your sound devices. You may have the option to choose. It depends. You may have the option to choose like stereo input, or I can't remember what it's called. There's actually a different option for that.
And when you shared your screen, did you select system sounds?
Ooh, good question.
I don't think I have that option. Oh, share sound. Coming from your computer as well as your shared screen. Ooh, okay. Well, we'll hope this doesn't backfire. Sorry, guys.
Hey.
Hi, I'm sorry.
Oh,
Sorry to be late.
not a problem.
I'm CJ Craig.
Of course you are. I'm Dr. John Fallow. This is Dr. Cynthia Sales and Professor Donald Huke.
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 Okay, and you are the Organization of Cartographers for Social Equality.
Well, we're from the OCSE. We have many members.
How many?
4,300 dues-paying members.
What are the dues?
$20 a year for the newsletter.
Let's start.
Wait, I want to see this.
This is Josh Lyman.
Indeed you are.
Josh, this is Dr. Fallow, and
Hi.
Ms. Mary Men.
Yes.
Should we begin?
Yes. Plain and simple, we'd like President Bartlett to aggressively support legislation that would make it mandatory for every public school in America to teach geography using the Peters projection map instead of the traditional Mercator.
Give me $200 and it's done. Really?
No. Why are we changing maps?
Because, CJ, the Mercator projection has fostered European imperialist attitudes for centuries and created an ethnic bias against the Third World.
Really?
The German cartographer, Mercator, originally designed this map in 1569 as a navigational tool for European sailors.
The map enlarges areas at the poles to create straight lines of constant bearing or geographic direction.
So it makes it easier to cross an ocean.
But
Yes.
it distorts the relative size of nations and continents.
Are you saying the map is wrong?
Oh dear, yes. Look at Greenland.
Okay.
Now look at Africa.
Okay.
The two land masses appear to be roughly the same size.
Yes.
Would it blow your mind if I told you that Africa is in reality 14 times larger?
Yes?
Here we have Europe, drawn considerably larger than South America. When it's 6.9 million square miles, South America is almost double the size of Europe's 3.8 million.
Alaska appears 3 times as large as Mexico, when Mexico is larger by 0.1 million square miles.
Germany appears in the middle of the map when it's in the northernmost quarter of the Earth.
Wait. Relative size is one thing, but you're telling me that Germany isn't where we think it is?
Nothing's where you think it is.
Where is it?
I'm glad you asked. The Peters projection.
It has fidelity of axis.
Fidelity of position.
East-west lines are parallel and intersect north-south axes at right angles.
What the hell is that?
It's where you've been living this whole time. Should we continue?
Uh-huh.
Okay. So that's a little bit about projections. Okay. And you can hear me again now, right?
Yes,
Probably.
yes, we can.
Great, thanks guys. So a little bit about projections. They are how kind of our interpretation or where these points and locations, how they're kind of assigned their locations on the map. So a projection determines the area, shape, distance, direction, kind of how these coordinates are translated into writing, right? So here's an example of the projection they were talking about, the Peters projection. You can see here, indeed, things are very differently distributed, and it may have more fidelity of area, which is the attribute that this projection focuses on, how much land mass is relative to each other. But it is going to be harder to use to cross an ocean because the surface of the planet is, in fact, curved. So thinking about projections, each set of geospatial data should come with what's called a coordinate reference system. So this incorporates the datum. So that's telling it how, when it was coding the information, what model it used for the shape of the Earth, whether or not the spatial data is in kind of a coordinate system or distances from something, geographic or projected, and the projection. So the mathematical transformation of these 3D coordinates into our 2D coordinates. So specific coordinate reference systems are referred to these days pretty frequently by an EPSG code. So you can maintain consistency between projects or between people. But the real takeaway from this, we're not going to get too nitty-gritty into projections, is that whenever you're reading or analyzing geospatial data, always check the coordinate reference system. Don't be like me. Here's an example of our iNaturalist data in its native projection. You can see here the EPSG 4326. And then if I reproject it to a different system, you can see it ends up here off the coast of Ecuador, which is not where it should be. And this will happen to you in your lifetime, I guarantee it. So always ask yourself when you pull up a new data set or start to run an analysis, what's the coordinate system? And there are 4 primary ones we talk about, or 4 examples here for California. This slide is mostly for reference. We won't go into it too much, but some of them, yeah.
Do you know why your data ended up in the ocean?
Because I switched it from WGS to NAD. Do you want to add something, Shane?
No, that's good enough. I was just curious.
Yeah, I basically told it to use a different model, a different equation here for the projection.
Okay.
Yeah.
Okay. Thank you.
Or people are seeing a lot of fungus out here in this mysterious patch of ocean. Could be, could be.
Could be.
Could be. So here's a few examples of coordinate systems. We have a geographic projection here with latitude and longitude kind of assigned using a grid across the surface of the Earth. We have something like Thiel-Albers, which is a pretty common data projection used when you're analyzing data statewide, and it has kind of an origin point, and then everything's based off of that central location. You have UTM, which has 2 zones for California, but might provide benefits when you're working in specific parts of the state. Great for analysis. And then we have some like real heritage situations here, like the state plane system, where they broke it into 6 sections. Pretty wild, but that particular data set, the native units of everything are in feet. So you won't run into projections that often in using geospatial daily, except for when you do, it will be catastrophic if you haven't checked it out correctly. So it's something that's can seem not that important until all of a sudden it really, really is. So to just kind of recap this geospatial data overview, it's data attributed with additional spatial information. This is location and projection coordinates. It can be vector, which is point lines and polygons and is spatially explicit, or it can be raster, where you have grids kind of covering a surface, things like imagery or satellite data, and that's spatially implicit. The coordinate reference system must be included, and the selection of which one to use should be based off of kind of what you're planning on analyzing and how you're planning on analyzing it. And finally, part of why we're talking about coding is because spatial information can be bulky, not easily readable by humans, and require specialized packages or software to read, visualize, analyze, and save. So that being said, there's a lot of information, but it opens up a whole world, literally, of possibilities. Geospatial data is available more widely and in more diversity than ever before, and increasingly so. It can be pretty overwhelming. And here's just a few examples of places you can access free or paid spatially referenced data. So things like the Land Characteristics Consortium, Living Atlas from Esri, Planet Data. We have a program called CalAdapt where we do climate data and things like the census data, and even your library has data. So it's not just for books anymore, guys. So that being said, when you're choosing data, there are some important considerations, especially if you're working on science or doing a project. So what data was used to generate the spatial information for your data set? If you're looking at something that's a density map, but then it was calculated per zip code, are you really looking at what you need to get the statistical significance you want for your analysis? If you're doing a remote sensing project and it looks a little too good to be true, maybe somebody applied a strategy to downsize something that actually is going to make your data not very meaningful. The minimum mapping unit. So what is the smallest object mapped? And I have an example here from CAL FIRE, where they produce a historical fire perimeter data set, which is pretty sweet. I'm a big fan of this. And it looks like it has really good resolution of data going back a really long time. But when you check the metadata, that is in fact true, but what was mapped varies over time. So if you're doing a particular sort of analysis, this can really pull something under the rug if you want to compare data from 1990 to the 2020s, but then it turns out you're missing brush fires over a certain size or under a certain size. And you can see here, there may be biases inherent in the data set, like none of these perimeters, they only start mapping them if they're over 300 acres for grasslands, but if they're on timberlands, they're mapped if they're over 10 acres. So checking your data source, how it was produced, who produced it, when it was updated, all of these are so crucial. Yeah. And what's the extent? Does the data set actually cover the full area you need? Does it cover the time period of interest? And when was the last time it was updated? Finally, how hard is it to access, manage, and store? Are you going to be able to regularly access this data? Do you need to download it all at once? Is it bigger than a terabyte? All of these are things you really should keep in mind when you're accessing your data. And also, always check the documentation and always record where and when you accessed the data set. Crucial. So I'm going to wrap up my section here with just a little thought on why you should try a coding workflow. So this may be a big, scary step for a lot of you if you're used to working in maybe an ArcGIS or QGIS environment. These are great. I'm not knocking it. Software like ArcGIS Pro and QGIS have what I call a visualization first philosophy. You can just drag your data set in and see it and take a look, play with the points, get the information really easily, get a look at distributions. It's easy to get started. You can drag and drop. You can stack a whole lot of layers and compare them really quickly. And that's because it does a lot of work for you behind the scenes. It's adjusting the projections. It has all these little tools where you just have to like click the drop down menu and adjust it. Beautiful user interfaces for the most part. Easy to make nice maps. Well, once you know how to make a map, it's relatively easy to make it. It's also easy to make a bad map, but easy to make a map. And then you don't actually need any programming skills. Oh, sorry, it's a little cut off here. It's really, really great for visual exploration of your data. But are you human? Have you ever worked through a whole analysis and then figured out you made a typo somewhere early on and it took like an hour to run? Have you ever clipped something to just like the slightly wrong size? Have you processed something in ArcGIS and then saved it in the wrong location or wrong format? Or have you done an analysis and then at the end you take a look and you find out all your degrees are in decimals instead of in meters, and you just are really, really sad. I have lived this many, many times, and this is part of what pushed me into the coding workflow. That, and of course, are you tired of never-ending toolbars and menus? Every time I open up ArcGIS Pro, the number of toolbars available and the frequency with which they just change a little tiny bit and you can't find anything anymore is just about all I can take. Well then, I am glad you are here today. I am glad you are hopefully sticking around for the next workshop because coding has so much to offer you. You get reproducibility for yourself and for others, so you can rerun that analysis. Just change that little parameter, set it and forget it. You can control things better. In Arc, when you use a tool, you click a button and then maybe you don't really know what it's doing. It just has a title of the tool. With this, you can really tell the computer exactly what to do, and for better or worse, the computer will exactly do that. It makes easily repeatable workflows. Make your adjustments, try again. You can document your methodology better, so not only you, but also anyone who reads your code can understand what you did and why you did it. It has automation. If you, like me, regularly download data for the entire state of California, it often takes 20 minutes, half an hour to crunch something. If you are good at coding, you can set something, you can repeat it, you can do it over lots of little chunks, and you can tell it to do it overnight, and you will not have to sit there. You will never set an egg timer for an analysis again. Coding has a table-first perspective. So if you are a data scientist and you're used to seeing things in a tabular format, this is wonderful news for you. It's so easy to think what you're seeing on a map is meaningful, but if you're like me, you really want to get down to the statistics and you want to check that things are looking good all the time. Tables for everyone. Finally, if you want to be a cool person, you can share code with your friends and colleagues. Amazing. Much, much harder to do if you're documenting a point-and-click analysis. So this could be you after you implement coding in your project. Stopping bullets, saving rasters from clipping in the wrong extent, really optimizing all you have to offer and accomplish. So should we take a little break here, Shane?
Yeah, let's take a little break.
Yeah. And if anybody has any questions, please feel free to post in the chat. I know that was a little whirlwind. And maybe I'll post a little question here as well for everybody about your prior levels of experience.
And I will add one thing about projections in ArcGIS Pro and QGIS. They project things on the fly, which is wonderful. But when you bring all your data together, you might be like, oh, they're perfectly projected. They're in the exact same projection. We're good to go. Be sure to check that because that is not the case often. And you never know who you're getting data from and what it's projecting in. So if you're going to do an analysis, project it all to the same projection before you do that. And we will hit that over and over and over again in the coming weeks. I just wanted to throw that out there. So can everyone see my screen okay? I'm going to assume yes.
Yeah,
So, okay, perfect. Yeah, so my name is Shane Fire. I've been doing GIS on and off for almost 30 years. I have done many different programming languages over the last 30 years. And about the last 10 or so years, the scientific community and the GIS world has shifted to Python. So Python is definitely a language that people are using for GIS and many other things as well. So that is one of the reasons we are teaching this webinar, this training series. So we're going to get into Python a bit. I'm going to try to cover the basics of Python. We're going to get into some of the things you're going to need to think about when using Python, and then we're going to go into the basics using a Jupyter notebook of actually some basics of Python, like different different structures, different data types, control loops, and things like that. If anyone ever asks me what's the most important language to take in school, I would just say programming language. I would just say a programming language, because in general, the important thing you need to learn when you do programming is know what you want to do. If it's in VB or VB.net, which I don't even think is a thing anymore, you need to know you want to do an if statement, or you want to do a for loop, or whatever. You can always look up how to do that on the web, but just knowing the question and what you want to do is what's important. So I just wanted to throw that out there right off the bat. So what is Python? So Python is a language that's been around a little over 30 years, almost 35 years. Was created by this person here, Guido. And the emphasis of it is on readability, simplicity, and versatility, as opposed to other programming languages at the time. And even programming languages now, Python is easily readable. It's easy to develop in. And there is an absolutely huge amount of packages and resources available to people that they can use to further their Python development. And often, just like in the R programming language, people are constantly building new packages and building in new functionality. So it's very powerful. One nice thing and why it's become popular is it's very versatile. It supports web development such as Django or Flask. It's commonly used in data science, and that's what we're going to be discussing today. One of the things I've been using it for recently in the last year or so is machine learning and AI development, automation, and many, many, many other things. A prime example of automation is a couple of years back, I was working on a project with people from NOAA, Berkeley, CDC, as well as University of Alaska and ourselves. We had many players. We had produced about 250 maps with this custom analysis, and we'd meet with the team, and about once a week, someone would be like, but what if we do this instead? And it got to the point where I was having to reproduce all these maps. By programming and doing automation, I could actually make that one little change, hit go, and it would reproduce all the analysis, all the maps in less than an hour. If I had to do that by hand, by the time the next week's meeting came up, I would have maybe have gotten it done, and I'd have to modify everything again. So Python's super important for that. Back to the slide. One thing I also point out here is community support. That's where I was talking about all the packages that are out there that people are commonly developing and that are available for us to download and use. And hopefully, if you really get into Python development and you're developing your own tools, that you then share back to the community so people can benefit from your work as well. Another thing here I point out is ease of learning. Most people on this call right now have said that their level of Python is a 1 or a 2. So I think that, the fact that it's easy to learn is really important. We're not talking Fortran, we're not talking C#, we're not talking anything like that. It is pretty straightforward. Seth, like you said, level 1, totally understood, totally understood. So what is the current state of Python? It is widely used in data science. Like I said, it's being used in artificial intelligence, web development, and automation. Major companies use it as their back-end programming language, and here are a few that are listed. For the last several years, I want to point out that we have been in the Python 3.x series. 3.x is constantly being developed. I have not heard any inkling yet of impending switch to a new version, Python 4. We are up to roughly Python version, I believe, 3.12. Does that sound right to you, Robert? And I know I put you on the spot.
I do believe so, yes.
Yeah, and I think Esri's using 3.12 and others as well. So one concept that we want to bring up, and we're going to be keeping this in mind in the next 2 sessions, are Python environments. So for those who don't know what Python environments are, they are an isolated workspace that includes specific version of Python, as well as other libraries and dependencies that you've installed. One of the major advantages to Python environments is when you're developing or doing data science workloads, you often need new packages. And when you install a package, it'll upgrade other dependencies, add new programs and things like that. If you're doing that to your base installation or your system Python, you could break it. And then you have to uninstall Python, reinstall Python, and hope you get everything back the way it was working originally. Whereas if you do a virtual environment or a Python environment, such as virtual environment or Conda environment, we'll describe the difference between those. You can actually spin up its own little container or its own little environment with a certain type of Python, all your packages and libraries. And if you break something, you've only broke that environment. You can delete it, reclone it, or recreate it, and reinstall your packages and bring it back up without causing any more problems. You can also isolate projects that have specific requirements and others that don't. Also, you may have projects that require very specific version numbers of Python and packages, whereas others may require different versions. So it's really important to have this option to have Python environments. To do that, though, there are at least two different ways to control your environment. There's the virtual environment system that comes as default within Python, that when you do a Python installation on your computer. The issue with that, however, is you can't specify the version of Python that it installs. It always installs what's on your machine. So if you have version 3.10 Python installed, you create an environment, it's going to be 3.10. If you have 3.12 and you have a package that requires, let's say 3.6, you have two options. Either you have to uninstall your main Python system and reinstall an older version, or you can use a different system called Conda, which is distributed through this group called, I think it's conda.org. I'd have to look it up for sure. And they have two main packages of distribution. One of them is called Anaconda and one is called Mini Conda. And what it does is with this package, you can install a virtual environment using Conda. You have the ability to say, I want this version of Python. So it doesn't have to be tied to your system type. So in my view, the Conda environment is the way to go in terms of giving you more freedom and flexibility for your development and for your data science. And it just makes it easy to do. One of the things I believe we're going to do, and Genoa, please correct me if I'm wrong, for session 3, we are going to be using something called Anaconda Navigator, which is a tool that you can install on your computer, which allows you to easily manage and create environments using Conda, as well as a bunch of other different scientific data analysis softwares. And it's really easy and straightforward to install and work with.
Yes, do not panic about environments.
No, do not.
We're going to walk you through it, and we're going to help you guys get set up. So when you are ready to do data analysis, you'll know how to get everything started.
Absolutely. Absolutely. So environments will make sense. Trust me. So once again, why are Python environments important and why we use them? Like I said, dependency management. We want to avoid conflicts between different projects that you're working on. You want to isolate libraries and packages straight off the bat. Productivity. You want to be able to create an environment and then recreate it, or whatever you use for your project. You want to save it and you want to be able to recreate it elsewhere, which allows you to work collaboratively. Like my colleagues, we can create an environment. I can get it working in development. I can then share it's called a requirements file, and they can rebuild that environment on their end and do the exact same analysis or use the exact same tools. And also it helps you be very flexible in your working with different versions and different dependencies. It's very, very important. Popular tools for working with environments are VNV, VN, it's a virtual environment, and that's built right into Python. I really haven't heard of virtual env in a while. I think VENV and virtual env, I'm not going to say they're the same, but they function very similar. And I can't remember which one, if they're both installed by default or not in a Python environment. Conda is a standalone, and I have not ventured into the Docker world, but Docker, you can also have containerized environments in Docker. So once you have Python and once you have Python installed and you want to start using it, you're going to have the need to install packages. Some of you are already using ArcGIS Pro. The thing about ArcGIS Pro is it has a package manager built into it, and it uses Conda. and it uses Esri's flavor of Conda. That's very important. And so you can go in if you want to install a package. For those of you who use Esri and ArcGIS Pro, the intended workflow for installing packages is use ArcGIS's package manager inside Pro. If that doesn't work, if that fails, use Conda outside of ArcGIS Pro. If that fails, use pip. So we're going to show pip, and pip is integrated into Python, usually by default. And it's super simple to use. You can search online and be like, looking for installation for pip of X package. Usually all you have to do is type in pip, in this case, pip install NumPy. It'll go out, figure out where NumPy is. It'll figure out the dependencies it needs, and it'll install it into your system. Super, super straightforward and simple. And that's in general. Go ahead.
If you aren't familiar with the concept of a package, essentially it's like a little toolkit. So part of why Python's so lightweight is you kind of only download the information or use the code that you need at a certain given time. And packages are just kind of little bundles of this code that you can then use to carry out lots of actions. So you just need to kind of specify what books you're checking out from the Python library for your project.
That is a really, really good point. And I should also mention that the Python core itself contains many built-in libraries. These are just additional ones that you're adding in. User created, usually open source created, so that you have you can bring in additional functionality that isn't default in Python. It's very nice and very handy. Pip is wonderful for that. I will say that there are some packages that are problematic to install. One of those is GDAL. Oh my God. Graphical. I can't remember. Graphic D. I can't remember what D stands for. Abstraction layer. It's a something that's commonly used in Python to work with raster data and to work with other types of rasters, including ArcGIS uses it in the back end. But if you go to install it, it almost always fails. Thank you, Genoa. It almost always fails when you install it in pip. But if you use the Conda install for GDAL, it works every time. So, there are pros and cons to using each. Like I've mentioned a couple times, the content package manager, that's a piece that comes with Anaconda and Miniconda and the Conda Navigator. And it's super easy to use. It's very similar in terms of the content, in terms of the code example. For pip, it's just pip install NumPy. For Conda, it would be Conda install NumPy. Really easy. And it also goes out, searches for all the dependencies that you need, what you need to update in your version of Python. And it comes back and it asks you if you want to do that. And then it updates your packages and gets everything working. Once you install a package, it is then available in your Python environment to use for whatever you want to use. It's really nice. And in general, Conda is used by data scientists, researchers, and others, especially those needing multiple language support, because Conda is not only used for Python, it is used for other languages as well. So the other thing we're going to really delve into, and this is one of my favorite things that has come out in the last decade or so, and that's Jupyter Notebooks. Python in general is command prompt, or there's an IDE, but it's text. It's all text coding. And with different IDEs or integrated development environments, you don't always get immediate feedback, interactivity between working with the code and seeing the results instantly. You type the code, you run it, you may get a line, but then you have to retype the code. Or you can save it as a file, you type it, save it, run it, type it, save it, run it, make a change. It's not really easy to do. Jupyter Notebooks kind of changed that. It was a project that I think someone from Berkeley, correct me if I'm wrong, but I believe Jupyter Notebooks were originally developed at UC Berkeley. And it's a wonderful system. It's interactive. You put all your data in a cell. Thank you, Dr. Kelly. You put your code in a cell, you run that cell, you get immediate output of what it is, what happened. It'll tell you if there's an error. You can then go back into that cell. You don't have to retype it. You can make an edit and rerun. So I'll show you that in a few seconds on how that works. And you can integrate graphing and charting and all this other stuff directly inside the Jupyter Notebook. And it just makes a really nice clean package that you can develop in, you can save it, you can export it, and you can share it with other colleagues, and they can run the same analysis. So for this, for the remainder of today, what we're going to do is we're going to delve into a Jupyter notebook that I've created. We're going to walk you through the basic building blocks of Python, and we're going to get all the way to tabular data that we are going to be using later on, the thing called pandas, which is a tabular representation of data. And we're going to show you how to work with the basics of pandas as well. And then the session 2 and 3 that are coming up in 2 weeks and 3 weeks or 4 weeks, I got to remember the exact timing, is going to build on the data frame and the spatial capabilities that we can expose and use. So hopefully this will all be helpful. And hopefully in this next piece here, you can stop me if we need to as we're going through. And we're going to slowly start building on expertise that you're going to need for Python programming. So with that, we're going to shift into practices. Any questions that you may have? I see Genoa put in the chat tables, because it's all about tables when you're not using the GUI. What was that? Would you say, Genoa?
I love them.
Oh, we all love tables. I will tell you that ArcGIS handles tables, but it doesn't handle really well working with tables, summarizing tables, and things like that. That's where Pandas data frames and going into Python itself excels. I will tell you that Python is my friend. It makes me happy when I have to go take things into Pandas and do analysis in there. So that's why I'm going to go into this workbook, and we are going to do what we need to do. Let me see. I'm going to put in the chat window right now. There is a Jupyter notebook that has been copied up to Colabs. If you were to go to that link, if you go to that link, you are going to see a Jupyter notebook, and it's going to be called GeoPython Session 1.
This is Google Colab, which is pretty cool. It's a way of sharing Jupyter notebooks in your Google Drive.
Yes, yes. And we're going to use that for today. For session 2, we are going to use an ArcGIS.com notebook, so an ArcGIS Online notebooks. And there might be some features I show you on my desktop using the ArcGIS Jupyter notebook just to show some advanced features on session 2. And then I believe session 3, we are going to be using Jupyter notebooks that are part of the Anaconda Navigator package that you'll be installing in your computer. Is that correct, Genoa? Or is it something other than Jupyter notebooks?
I think it's Jupyter notebooks. Sorry, I'm typing at the same time.
Understood.
Yeah,
Okay.
and I would recommend once you open this up, go to File, and then save a copy in Drive. If you're interested in playing with this notebook in your own time, making edits that you can save, I would recommend saving a copy. It'll open up another tab in your window called Copy of GeoPython Session 1, and then you can kind of go nuts.
And I tried to put basic stuff you're going to need in Python. So if you haven't used Python a lot, this might be an easy notebook for you to refer back to see about how to create variables, how to do for loops and those type of things, and just make a really nice and simple way for you to refer back to do some of these things.
Let's take a couple minutes just for questions and for people to open it up. And once you have it open, can you just put a thumbs up in the chat? Is that how we do it? Yeah.
Yeah. So perfect. Let's get started here. And I've highlighted on the screen right now some of the main things we're going to cover, the basics. And then the other 2 items going to be creating your own custom function, because that is a very powerful piece of Python programming, is you can create user-defined functions. So if you're familiar with like Excel, where you can like, equals type of function name, put in parentheses what you want, and you get something back from Excel, you can create those type of things in Python programming, but you control every bit of it. So you can create custom functions that do really important specialized things, and you can really help that improve your workflow. So we're going to show you the basics of a function, and then where we really hit a lot of detail is going to be working on Pandas data frames, and that'll be towards the end of this piece that we're going to work on. So the first piece we're going to tackle is Python basics is variables and built-in data types. If you're doing basic programming, you're going to have the need to define variables. And variables in Python are really easy to define. So here we have a simple string variable. You can see I'm saying the name of the variable is going to be called name, and it could be anything. It could be anything you want. I believe there are some special characters you can't use, but it'll tell you that. In this case, I can use name. The equal sign says name, and you want it to be equals to whatever you put after it. In this case, it's going to be a string, and the string is my name. So if I run this line, name variable is going to have the string applied to it. In Python, if I say print and then in parentheses the variable name, it'll actually print that out for me. One cool thing about Jupyter Notebooks is that you don't have to say print. You can just put the name of the variable at the end of that cell, and when you run it, it'll actually print it out for you. And you can see here it's a string. But I also see the output of the print statement, which is the first example of my name. So that is defining a string. Something, and yes.
Just one note, if you made a copy, you can edit the notebook. So try putting your name in instead of Shane's, unless you really are dedicated to this mission. And then also you can hit the little play button to the left of a cell to run it, but you can also press Control Enter, and that'll run a cell for you.
Thank you very much, Genoa. And I'm kind of partial to my name, so I put it there, but yeah, put whatever you want, and it'll give you the output there. So then the next piece, so that's working with strings. And the next thing is we're going to show you how to work with numbers. So here, this is an integer value. So I'm going to say make the variable num equal to an integer value of 20. And once again, if I hit print num and I say print, but now I can do math, I can actually do a calculation based on that because it's a number. And if I run this, as you'd expect, the number is 20, and that's what I'm printing out, num 20. But then I told it to multiply it by 2, and now you see it's 20, it becomes 40. So mathematic operations work just like you'd expect. And feel free to play with that a little bit, but it's pretty straightforward. But keep in mind that because we defined it as an integer here, we did not have like a 0.0 to make it a float. It assumes it's a float and it becomes an integer. I mean, it assumes it's an integer and it uses it as an integer unless you specify different. If I go in here and add a decimal place, Python assumes it's a float value instead of integer, and then everything after that will be a float, such as that.
And if anyone's notebook isn't running, try hitting where Shane says RAM disk with the green check mark. There should be a button, and if it says connect instead, just click on it and it'll connect you.
Thank you, Genoa. So we've talked about strings, we've talked about numbers, integers, and float. And we'll hit that again, the numeric types. But then there's also Boolean, so true and false. Often when you do a test for something, let's say an if statement, so it does, if num, and don't put anything like equals this. If you just say if num, it'll test if it exists, and that'll be a true or false. If you say if num equals 20, that's going to be a true or false. So it's a Boolean is a common thing you're going to use. So you can set those to a variable and then test for it later. The important note, and this is in the pro tip, is that Boolean types are case specific. So a capital true is different than true. So capital true is a Boolean variable. Whereas if I do this, I'm probably going to get an error. Well, I'm definitely going to get an error if I do that. Because I'll get an error because I'm telling it to set something equal to a string true instead of a Boolean value, but I haven't wrapped this in a string. So true and false need to be capital. And in the Jupyter Notebook or in the Colab Notebook, it'll actually show you that it's formatted correctly because it has a different color for the type of variable it is. So here, choice is true. I'm printing it's true. And then I have a simple if statement. And in programming, you are going to do if statements quite a bit. So here I say if the variable choice, if it equals true, print this. Else, that meaning it's false or doesn't exist, the choice is false. One caveat, one thing to pay attention to when you're programming in Python and almost any language is when you're testing something in an if statement, this right here, if I just say choice equals true, is not the same as equals equals. Choice equal true sets a variable. Choice equal equal tests a variable. and that's important to note. I will tell you, my son was taking Python programming in senior year of high school. He was having a problem for a day in his programming. And of course, he asked his dad, what's going on? I walk into his room and that was the problem he was having. So be really careful when you do a test. And I can't tell you how many times I've had that problem. Okay.
Half of the
so
battle in Python is, did you close your parentheses?
Oh God,
So
yes.
there's a reason it's a language, and it's how we communicate with a computer using symbols that usually mean something else. So bear with us. These are kind of building blocks here.
That's a really good point. And it's another good point is you will often forget the closing colon, and indentation is very important in Python. So if you find something that says improperly indented, check your indentation. If you're in an if statement or you're in a function, everything needs to be indented inside that statement because that's how it knows that it needs to do something or do that activity inside of it. Okay, so we've talked about Boolean, we've talked about strings and basic numbers, and now let's talk about integers. We described this a little bit. So num10 is an integer. The important thing to note is you can actually convert those. You can change the type if you need to. But right here, so if we look at this, we're saying num is equal to 10. We print it. What are you going to see is indeed none is 10. If you then say, give me the type, it says it's an integer. The next one we're defining as a float, so 5.1. If we say, what type is it? It'll tell us it's a float. And if you want to convert something from a float to an integer, there's a simple function to do that called int. So if you do int the variable and you assign it to a new variable, you can then look at it and you can see it now became 5. It truncated the 0.1 off, and it's now an integer value. So you can very easily work with numeric values. And in a similar vein, you can do the same with floats. You can convert floats back and forth between float and int just by calling the integer. Let me see, where is it? Actually, I don't do it here. You just call int instead of float, or you can turn it into a float by saying float. Something to note when working with strings, and you will make this mistake. I do it all the time still, is when you define a string, you can use single quotes or double quotes. They both work the same, but you can't mix them up. You can't have a single quote and a double quote. It will error on you. So be careful on that, and it'll actually flag you and tell you it's an error if you try that. Such as that. Okay, so now we've talked about variables, and now let's talk about working with strings and numbers. This is something you'll do in your programming and your different loops that you're going to be trying to do. You can easily concatenate things together just by doing a plus. A plus will concatenate text together. So you can say howdy plus partner, and if you run this, it's going to say howdy partner. It combines it together. What do you think is going to happen here, though, if I tried to concatenate a string, an integer, and a string? It gets unhappy, and it says, you have an error here, and it's because you're trying to concatenate an integer value to a string. So what you need to do is you need to cast that to be a string, just like above where you could change it from an integer value to a float by typing in float, or vice versa, a float to an integer by converting it using the int command. You can convert a string to a number to a string by typing in string. If I do that and run this command, it now works perfectly. The next piece of this I want to show, and there are many ways to do this, and this is going to be string substitution. I know, Genoa, you do a different method than what I do here. String substitution, the way I do it, you have the string that you want to substitute into. You put in this case, a %s, and %s means I want to substitute a string. And then you put the % followed by what you want to add in as a string. If I run this, it's going to do that. It's going to insert outstanding into that space. And you can do that with multiple placeholders. Here's the first one. Here's the second. If I run this, you can see it put those in, number 1 and number 2, in those places. One thing you may wonder is, well, can I do that with integers? Can I do that with floats? You know, can I do that with other data types? The answer is yes. So if I was to go in here and change this to I for integer, and I put in a 1 instead of a string value, it'll actually insert that as a string. If I change this to an F for float, keep the 1, run that, it adds it in as a float value. So you have formatting capabilities by changing that from an S to an I to an F, whatever it is. Okay, so that's string substitution. You'll find that handy when you're doing programming in loops and things like that. The next piece, and I'm looking at my time, is there are lists. These are going to commonly be used for programming. A list is a series of items that you can work through. In this case, it's going to be words. So we got 4 things inside this list. And if I run it, you can see them. You got foo, bar, baz, tux. They are sortable because lists are mutable. In other words, you can change them. So I'm going to sort this, and it's alphabetical. Now you can see it's gone through and sorted that. And you can then loop through these. Here's a basic for loop for I in the list of A. And if I run that, it's bar, baz, foo, tux. It works. It sorts as you'd expect. You can also go through and tell it to give me the first item, give me the last item, give me the first through the second item, and so forth. You can go through and tell it to give you different items from the list by using indexing on that list.
Yes, and a really fun fact about Python is that it starts numbering with 0.
Thank you.
So 0 is in fact foo in this list.
Yes, yes. Yeah, Python is 0 based. That's a really good point. If you want, you can test this here, but I'm just going to slowly keep going. So lists are mutable. You can add things to a list. You can delete things into a list, and you can resort them, whatever you want. Tuples are not. Tuples are immutable. So once you create them, you cannot change them. So in this case, I've created a tuple, and it has these items in it. You can still index it just like a list. And you can loop through it just like you could with a list, but if I try to sort it, it's going to error because it's not mutable. That's really important if you have something you don't want to have change, but you need to be able to iterate over it. A couple quick things. We've talked about lists. We've talked about tuples. There's also something called range. In a range, you can say, give me 10 values. In this case, range 10. If I loop through that, it's going to give me the values from 0 to 9. And that's because it's going to go from 0 to the stop value, which is 10. It doesn't give you 10, it stops at 10. So we got 0 through 9. If you want specifically 1 through 10, you have to play with it a little bit. You're going to say the range is going to start at 1 and stop at 11. And that'll give you 1 to 10, as you'd expect. So once again, 0 based. You also have more flexibility. You can say, I want a range, I want values from 2 to 10, but I want every other value. So you can say start at 2, go to 11, and skip every other. So you have really fine-grained control of what your range looks like and what your numbers look like. Okay, so we're moving quick. So the next piece here is going to be iterators, iterations and loops. This is a common thing you're going to use. So here I'm going to loop through. I got a for loop. So I'm saying for each item in the range, I want to print it. It's that simple. The important thing here is the for, what the variable you want out, what you're looking in. That could be a list, a tuple, or a range. And you have to close it with a colon, indent, and then what you want to do. So there you go, 1 through 9. In a similar vein, I can go in, I'm going to set x equal to 0. I'm going to say, in this case, it's not a definite loop, so it's not just going to go to 10 and stop. This one is going to count up, and if I never hit 10 for some reason, this loop will not stop. So I'm going to say x equals 0. I'm going to say do it, basically do while x is less than 10, keep going. So if like I said, if x doesn't ever equal 10, this loop's never going to stop. If I run this, and the important thing is I'm incrementing x up by 1. So if I run this, I have the same result, and I'm not going to do it. If I went here and if I said increment this by 10 or more, let's say that would work. If I wouldn't increment this up, this thing would just run and run and run and run and never stop. So I don't find myself using while loops very often. So we've talked if. Now let's quickly hit on for and if statements, conditional statements. We've hit fors, and up above I showed you an if, but here you can say if. So if I is equal 5, do something. In that case, print this. You reached number 5. Otherwise, you're not going to print anything. All right, so you're just testing. Until that I value equals 5, just don't do anything. Just print out I. So it's a way to conditionally go through and decide which way you're going to go. Think of it as a conditional branching in code, because that's what it is. If I do something similar and I do an else, so not only am I saying if this, I can say if 5, else do this. So you can tell it different pieces of logic. So here I just said print 1 if it's print I if it's not equal to 5. In a similar way, I'm saying print 5 again. And then instead of just saying print I, I'm giving it something else to do. So it has the same result as the one above. The caveat to that, there's something called else if. So if I equals 5, do something, but then I can have another if statement after that. If, else if in other languages, I equals 6, do this. And you can have as many ifs as you want, just a way to nest up a bunch of if statements. This is handy to do when you're really doing complex programming tasks. And here's how that works. Okay. We're getting down to functions. Functions are something that are really important for data science. They're really important for being able to control your logic and be able to encapsulate different code functions that you're trying to do, especially things you're going to do often. So I'm going to quickly show you a really basic function and the different parts of a function. So when you create a function, you need to define it. So def, which is basically calling function in JavaScript, but def the function, here's the name of it that's going to be called. And then in parentheses, you're going to put parameters. So the parameters are what that function is going to be expecting. So this function expects a list and an optional parameter of a multiplier. And you specify an optional parameter by putting the name in and assigning a value. That way, if it's not supplied, it uses a 1. So what this specific function does, you set the product value equal to 0, you loop over the list of numbers, and it adds them together. And if there's a multiplier, it takes each value, multiplies it by the multiplier, and adds it to the product. After it loops through every item in the list, and the other important thing about a function is you have to return something. In this case, I'm returning product. So I bring in a list, I have a multiplier, it works through it, and it returns the sum. That easy. A function can return any Python object that you pass in and work with. You can pass it in and you can bring it back out and save it as a variable and continue in your program. So in this case, I'm just going to run this function. It's going to load it into memory. And then I can pass in a list of 4 values, 1, 2, 3, and 4. If you add all those together, it equals 10. And if I run this, you can see the first time in, it equals 10 like you would expect. If I do a multiplier of 10, it equals 100 because every one of those values gets multiplied by 10. Really straightforward. You will use functions a lot. Feel free to play with that if you'd like. The next piece of this is pandas data frames. This is really tables. Genoa put tables in exclamation points because that's how we think about it. In Python. It's all about tables. Thank you, Genoa. So in Python, we're going to use tables, and that's going to be using the package called pandas. Pandas is the tool or the package in pandas is package in Python that allows us to treat data, NumPy arrays, and other data types as tables and work with them in a table format that we understand. And it looks similar to Excel when we see it inside of a data frame, inside of a notebook. So here we're going to load in a default data set coming from a GitHub repo. And this is just some 150 values of different iris measurements. Not irises as in eyes, but iris as in the plant. So here I read that in. I say I load pandas. Once pandas is loaded into the Python environment, I can then use pandas, in this case PD, and I can say PD reads CVS or CSV, comma, separated value file. I'm passing in the path to that file. It's going to read it in and open it in a data frame called iris. If I run that code and it displays iris, I can see there are 150 rows, there are 5 columns. Those columns are length, sepal width, petal width, and the species. So that's the data we're going to quickly work with. So this is a data frame and it's called iris. You will do something similar in the coming weeks, but with tabular data that has spatial information. If you want information about rows and columns, let's say we didn't get that reported out because we had it only give us the beginning or end of the table, you can write and you can run the function called shape, and it'll tell you the number of rows and the number of columns when you call shape. So it's really easy to work with these tables. One thing you may find, and it's really important to be able to do, is you may want to add new data to your data set. So in this case, I'm going to quickly calculate petal area. So I'm saying, make me a new column called petal area. I want to take the product of petal length times petal width to come up with the area. If I run this cell, you can see right here, here's petal area. It's been added, and it is the multiplication of petal length and petal width. I've now created new data inside that data set. If you did this in ArcGIS Pro, there'd be many steps to get to this point. So now I have this new data set with a new field or a new column. What if I want to subset data? This is something you're frequently going to have to do. So I'm going to show you 2 different methods for subsetting data. You may want to subset data in terms of subset by rows or filter by rows, or you may want to get rid of columns. You may not need all the 6 columns that we have here. So in this case, I'm only going to pull back the rows where the species of iris is setosa. So I'm saying, look at the iris data frame, and I want to look at the iris data frame column of species, and it has to equal setosa. And I want it to be saved to a setosa data frame. If I run this, I will get just the setosa data. And you'll notice here, I also said, give me the first 5 rows by typing in head. If I type in head and then friends add a value, I can get the first 10 rows or whatever I want. So it's an easy way, instead of showing 150 rows or whatever you have, you can only just bring back a subset so you can make sure it's doing what you expect. So that's working with rows. If you want to do the same thing, but this time with columns, what you will do is, instead of saying a field, a row or a column equals a value, all you have to do to subset columns is pass in a list of the column names you want. So in this case, I just want to bring over the petal information. And those would be petal length, petal width, and petal area. It's a list inside of the iris field list or the iris column list. And if I run this, you will see that it's now called iris petals is the data frame. And it only has the petal columns. And I said, give me the last 5 rows. That's why I put to that. So now I have, you can see I can easily work with the table. One thing we want to show you, and I apologize, it's 2:29. Hope y'all can stay on. Tristan, are you okay staying on? Is everyone okay staying on a few more minutes? I'm going to assume yes. Okay, so now we're going to show you how to work and join data frames. So we're just going to create a fictitious other data frame, and it'll show you some other steps of how we can work with data. In this one, I'm going to take that iris area field. I'm just going to create that, pull that out, and save that as a new data set called iris area. And then something you will have to do most likely when you work with data frames is you're going to have to rename a column. So I pull the data out, save it as a data frame that only has 1 column. And now I'm going to rename it. So I'm going to rename petal area, and I'm going to rename it petal joined instead. And I'm going to do it in place. So I don't have to create a new data frame to do it. And if I do that, here's what I get. Same data, the same values, but now there's a new name for it called petal joined. So now what I end up with is I have 2 data frames. I have iris petals, and I have the iris area data set. iris area data set, and I'm going to join them together based on their index value. You can see here, there's the index values, 145, 146, 147. Down here, 145, 146, 147. So they actually match up with each other because I haven't re-indexed. So I can join based on that. So I'm going to go in here and I'm just going to do this thing called join. So I'm going to create a new data frame. It's going to be called iris join. I'm going to start with the iris petal data. I'm going to join iris area to it. Because I'm not specifying a left suffix and a right suffix, or in other words, a column in the iris petals data set that I want to join on the iris area data set or the petal area data set. As long as I haven't specified these two, it's going to do it based on index. And if I run that, it joins them together as you'd expect, and you can see the values actually join up properly. If you need to join them on a different column names, you just change these values and use this piece of code instead. Sean, thank you for putting the evaluation survey into the chat window. So feel free before you leave. Hopefully you take that survey for us. We do use that information. So now you have an iris join data set. The last couple steps here, I just want to quickly show. If you want to look at descriptive statistics for your data frame, what you can do is you can very easily just pass in something called .describe. And it'll actually go in and give you all the descriptive statistics for each one of the column names inside your data set. And you can save this off as a different data frame if you want, and then save it from there as well. But if you want finer control of doing a group by, if you're used to like databases where you do group by queries, or you do case summaries inside of ArcGIS Pro, you can use a group by object. So here we're saying take the iris data. We're going to do one of those here. We want to group by the species field, and we want to take the mean value of all those different species. And I'm going to save it as a new data frame. If I do that, what you end up with is you have a field here for species. So Setosa, versicolor, and virginica, and you can see the mean values for each one of those things. Really easy to get statistics for that. You can further expand on group by objects by using an aggregate function. And you can put in, I want to look at this field. I want to calculate mean and standard deviation. I want to look at this field and do the same thing. And you can build out your statistics that you want. And if you run that, you get something similar, but now you see sepal length, sepal width, petal width, and you see mean and standard deviation for both of those by species. So you can really start to slice and dice your data and make it more and more meaningful. One of the challenges here, if you wanted to try it, and I'll just do a quick copy and paste here. One of the challenges if you want to test it is you can see if you can try to calculate a more efficient way of calculating statistics, and that is to use the describe feature. So instead of aggregate or instead of .mean, if I just type in describe, it'll give you descriptive statistics with all that information for each species, and you don't have to build it out. So there's many ways to do that. But it really gives you the power of how you can work with data frames and what you can do with data. So once you've done all this work and you've crunched all your data and it's functioning, how do you get it back out so you can use it elsewhere? There are easy functions to do that. You can export your data out as a CSV file. You can also export your data out as an Excel spreadsheet. When you're working with spatial data, you can export your data as a shapefile, GeoJSON, file geodatabase, feature class on ArcGIS Online, all sorts of different things. But in this case, we're just going to show you how to save them as a CSV file or an XLS file. Once you run that field, if you go to the folder button, you will see you now have a mean CSV file and a mean XLSX file of that data frame. So it works really well, and you can do a lot with data frames. Okay, so that's the basics of working with Python data frames and variables and constructs, whether it be ifs and for loops and stuff like that. So please look this over, and if you have any questions, reach out via office hours. and Sean Hogan put that link in the chat window. Please reach out to us, and we will get back to you and try to help you and make sure you're up to speed before the next workshop. And I believe the next workshop's in 2 weeks on the 21st. I look forward to seeing you, and please fill out the evaluation, and we look forward to meeting with you in 2 weeks.
Yep.
Thank you
And
for
again,
attending. Go ahead.
we set up workshops 2 and 3. So workshop 2 is going to focus on still working kind of within an Esri or ArcGIS online workflow. So if your company or your business, if you work for A&R and a lot of your data is already kind of in that environment, that's a great experience for you. And then I'll be doing an open source, so kind of more like this Jupyter Notebook we have now session using packages that aren't affiliated with Esri and use kind of different file formats the week after. So
Yes.
feel free to come to both if you want to get a taste for it and make a decision. If you have a specific objective or workflow already in mind, pick and choose. But
Yes.
we would love to have you there, and thank you for coming today, as Shane was saying.
Thank you, Janelle.